In this video, we talk about the graph of the log function. The logarithmic function. Okay, so the approach that I'm going to take is that we begin with sketching y equals 2 to the x power. And I am going to plot some points. 2 to the 1 power is 2. 2 squared is 4. 2 to the third is 8. 2 to the 4 is 16. So we double each time. 2, 4, 6, 8. Going the opposite way, we progress by half. 18, 16, half of that is 8, half of that is 4, half of that is 2. Then comes 1. Then comes 1/2 when I divide by 2 each time. Then 1/4. All right, so let me sort of think about how much space I need here. But I guess I'll go with what I have here. Okay, so I have that 2 to the 0 is 1, and then moves up to 2, then 4, then 8. It grows very quickly. That's part of the one of the aspects of the exponential growth, is that it grows so quickly. All right, so this is the function y equals 2 to the x. Now the video is called the graph of the logarithmic function. The logarithmic function is the inverse of the exponential function. When I say it depends on which base we're using. The function y equals log base 2 of x is the inverse function of y equals 2 to the x. And so the points on the graph of y equals log base 2 of x are the same as those of y equals 2 to the x, but with the coordinates switched or flipped. Not flipped, switched would be the right word. Swapped. Maybe swapped. Swapped would be a good one. Okay, so what do I mean by that? So I'm going to swap the coordinates. And so above here, this is x, and then y equals 2 to the x. So somewhere along the way, I need to make a chart for, maybe I can do it here, for y equals log base 2 of x. So it's just, I'm trying to fit everything in a little space here. But let's do log base 2 of x. What I'm going to do is I'm just going to take these two coordinates here. I have -1/2, 1/4. Say that's over here, or sorry, -2, 1/4. And I'm going to swap those. Then I have negative 1, 1/2, and I swap those. So I change the order. Then here I have 0, 1, and I get 1, 0, then 1, 2, and I'll write 2, 1, and 2, 4, and I'll write 4, 2, and then 3, 8 corresponds to 8, 3. I didn't do 4, 16, it was off the graph. Okay, so did I do this right? Yeah, 8, 3. Okay, so this is the logarithm. This is the inverse. The inverse, this is true of any function in its inverse. To find the inverse, you swap the x and y. So when you have y equals 2 to the x, this is the same as x equals 2 to the y. Sorry, x equals 2 to the y. That's what y equals log base 2 of x means. It means x equals 2 to the y. You swap x and y. So then when you plot points, maybe I'll use red this time, I change the coordinates. So I have 1, 0, 2, 1, 4, 2, and 8, 3. And I connect those. And then over here, I can just do these also. But it's just a little smaller space, but I can just put those also. Okay, so this graph right here is y equals log base 2 of x. And this is how you can find the graph of any inverse function. And also, the graph of an inverse function is a reflection around the line y equals x. So if I do sketch the line y equals x, the inverse is a reflection around that line. So let's then look at some ideas that we have for these two functions, some little facts. Let's see if I can also see if I can organize this. Y equals 2 to the x. Y equals log base 2 of x. Okay, so if I look at domain of y equals 2 to the x, it's all real numbers. Any real number will work there. If I look at range of y equals 2 to the x, what do I get? It's only those y that are greater than 0. Now, when I swap x and y, that's going to swap the domain and range. So what was the range of 2 to the x becomes the domain of log base 2 of x. So the domain, all right, so, okay. Domain, when I'm using x and y, domain corresponds to x, and I get r. Range corresponds with y, and I get y greater than 0. Then when you switch x and y, which is what you do when you have an inverse function, you're going to swap these domains and range. So this domain then becomes all x greater than 0. And besides, you can just look at this graph. X is always greater than 0. It's never 0. It's never less than 0. And then for range, the domain of 2 to the x becomes the range of log base 2 of x, and that's r. That one is not so clear from the graph, because the graph of logarithm seems to be growing, but it grows very slowly, and someone possibly by looking at this, just by looking at patterns, might think that there's a horizontal asymptote, but there isn't. It just keeps going up, but it goes very slowly. Y to the 2x is increasing, and so is logarithm. y equals 2 to the x has a horizontal asymptote. The horizontal asymptote is the x-axis. You can just see these things. Look, I mean, that's why I sometimes, don't write all this stuff out, because you can just look at it and see, oh yeah, okay, I see it right there. So there's the horizontal asymptote. But what that means when I switch x and y, so the x-axis is the same thing as y equals 0. When I switch x and y, I get a vertical asymptote. Which is the y-axis, and that's the same thing as x equals 0. So you can write down all this stuff and memorize it, but I think it's really good to look at this graph of logarithm and actually be able to do it sort of quickly. What are the big features? What I think we should look for is the general shape, that it's increasing, but it also has this curve down. They call it concave down. And also we look for the vertical asymptote. And the x-intercept there. So we'll try to memorize that. Now this is base 2, but as long as your base is a number greater than 1, you're going to get something very similar. Or depends on what you think is similar, but the vertical asymptote will be the same. The intercept will be the same. It'll look pretty much the same unless you have a computer to compare to two different cases. So we talked about another base, which is, or another number besides 2 that we can use for an exponent. This is 2 to the x. There's also something we use, which is e to the x. And we can also use e for our base here and have a natural log of x. And maybe we'll just do that right now. So if I have the number e, the number e is approximately 2.718. This is Euler's number, and it keeps going on. So when I put the dots, maybe I shouldn't put the squiggle, because it means it keeps going on, and that maybe is the exact number. But if I sketch y equals ln x, which is the same as log base e of x, if I sketch that, it's really almost the same graph. And if I ever get stuck, I can sort of just do log base 2 of x as a guideline. It won't be exactly the same, but it's very similar. Okay, so what we're looking at is that we have 1, 0. We have the same vertical asymptote. It's increasing. And, e is between 2 and 3. And if I were to use a computer to sketch the logarithm graph and on the same plane log base 2 of x, if I were to sketch those, I would see a difference. But what would be the same would be the intercepts and the asymptotes. All right.